I'm the co-director of Berkeley DeepDrive, which is one of the leading research institutes in the field of AI for automotive industry. I'm also a chief scientist of Applied Intuition, leading the effort of AI research. So today, I'm going to share a bit more thoughts regarding how we are going to change the autonomy with foundation model, especially with the language modality, from some latest research of what I'm doing at UC Berkeley. So a bit overview regarding our research center. So we are focusing on AI for autonomy and mobility. And actually, we've been working with a number of Berkeley faculty as well as leading industry partners, including many of you sitting right here. And we also work intertwined with the Bayer Research Center, working on more general and fundamental AI research. And for myself, I've been covering several fields of research regarding machine learning and AI, intelligent transportation systems, robotics and control, as well as the computer vision. And I'm working at the intersection of the four fields to enable scalable autonomy stack, as well as the development pipeline. And several of my papers has been awarded in the flagship conferences and journals in those fields. Regarding the scalable autonomy, actually, what we are trying to do is to solve numerous problems for mass deployment of autonomy in a viable, affordable, and sustainable way. And actually, we are thinking about this from mainly two perspectives. One is the onboard AV stack. So we want to replace the tedious rule-based methods into more differentiable stack. And in Berkeley DeepDrive, we will always have the mindset to integrate our algorithms with more automotive grade and cost-effective sensor suite, as well as a computing platform. And we also want to have the development pipeline to be more AI-driven. So we want to construct pretty efficient and automated data pipeline and engine, as well as to use closed-loop simulation to replace the heavy road tests, which can be costly, risky, and inefficient. So we would like to design some differentiable stack as well as AI-driven development pipeline to deal with various kinds of onboard tasks from perception to planning, as well as the offboard tasks related to data engine simulation and training test iterations by taking into account a lot of multimodal stream. And actually, foundation models, which can be trained with broad, large-scale data to be applied with many kinds of downstream tasks, can be a pretty suitable and powerful tool for us, especially when combined with the language modality. So first, let me talk a bit about the differentiable stack first. So actually, when we are thinking about the input side of the differentiable stack, there could be multi-view camera information, multimodality sensor information from both camera and LiDAR, as well as the information across the temporal domain. And actually, in our work, time will tell, we are trying to perform temporal fusion from the multi-view camera, especially taking into account relatively long-term historical information to facilitate our current frame 3D detection. And in our sparse fusion, we are also trying to utilize the information with sparse candidates, sparse representation to facilitate early-stage LiDAR camera fusion with significantly improved performances. And when talking about output side of the differentiable stack, when we are generating actions for planning and control, actually what people usually do is to employ some imitation learning-based method to learn from demonstration data of the human expert, for example. But the problem is there could be a lot of out-of-distribution data points that we can encounter in the real world. And there are also a lot of under-demonstrated requirements that we have to consider that cannot be well represented in the demonstration data. So what people usually do would be taking the prior policy and somehow further train that or refine that with closed-loop simulation for robustification or customization, and maybe adapt that in the real world. And some conventional paradigm would be construct some, for example, so-called Q function for the customization by adding some additional reward, considering the under-demonstrated requirements, on top of some prior policy reward to be estimated. But the problem is, it's pretty hard for us to accurately estimate what the prior policy reward would be with the implicit way. And that's why we are trying to construct a new paradigm called residual Q-learning. And we are trying to do some mathematical manipulation so that we can create a residual Q function that can directly take into account the pre-trained prior policy itself instead of estimating any reward of the prior policy on top of the additional reward, so that we can customize without explicitly knowing the reward from the prior policy in a systematic and theoretically sound way for customizing our differentiable stack. And after talking about the input and output side of the differentiable stack, next let's talk a bit about language incorporation. So it would be desirable for us to incorporate relatively fine-grained description of interactive behavior and scenes with the differentiable stack. But a prerequisite would be constructing the corresponding data set for this. And that's why we have been constructing this WMOB reasoning data set, which contains relatively large-scale language QAs with 3 million pairs associated with over 60,000 total scenes. And it contains pretty comprehensive and fine-grained interaction descriptions. So actually, we are building the data set on top of the Waymo OpenMotion data set, which contains a lot of highly interactive driving behavior with selected interaction pairs, as well as corresponding HD map. And we are utilizing large language models to automatically generate a lot of QA pairs with scene description as well as the interaction reasoning. And we are also having human to verify that to further improve the accuracy of that. And here is one of the examples showing what is contained in the data set. So for example, there is an ego agent making a protected left turn. And there is an agent, number 1, which is trying to make a right turn, having potential conflict with our ego agent. So our language QA pairs can provide interaction and intention descriptions with the implicit right-of-way, explicit traffic rules, driving situation, all those kind of things. And we are trying to incorporate that with some widely used behavior prediction models, such as the multipath++. And we are trying to compare with or without such language description, what would be the difference of the performances. And in the quantitative results, you can see that we can further improve the accuracy of the behavior prediction. And in this qualitative comparison, we can also find that we can make much less aggressive prediction of the ego agent making an unprotected left turn when encountering another vehicle going straight forward holding the right-of-way. Okay, so after talking about input-output side of differentiable stack as well as language incorporation, next let's talk a bit about AI-driven development pipeline and how foundation models will be facilitating that. First is about the data engine. So for data engine, actually, when we get huge amount of data obtained from the real world, there will be a large portion of the which can be a bit useless for us, and we don't want to waste our storage or labeling efforts or uploading bandwidth for that. And it could be even more ideal if we can perform this on board with edge computing with a single pass inference. So that's why we constructed such kind of active data selection framework to take advantage of general purpose model pre-trained with internet data. And then we can utilize the feature space and attention inside to help us design some mechanism with a single pass inference so that we can select the data from the stream or even onboard. And after selecting the useful portion of data, what we are considering next would be how we can label them or train our model. So there could be a relatively small portion of the data with human labeling. according to, like due to our limited budget. And there could be a relatively larger amount, which is unlabeled. And what we are thinking about this is we could try to utilize the human label data to train some so-called teacher to auto-label the large amount of unlabeled data and combine that auto-label pool with the human label data to train a so-called student here to be deployed onto our autonomous vehicle. And we can employ semi-supervised learning to simultaneously optimize both the teacher and the student side. And in our work, we are trying to design a multimodality semi-supervised learning framework to take advantage of both 3D and 2D modalities so that they can help with each other with the 2D, 3D matching mechanism to improve the auto-labeling accuracy. And with such kind of multimodality semi-supervised learning framework, when applied onto the real-world data set, we can clearly see its superiority, especially when there are a lot of like false positives in the single modality semi-supervised learning. We can directly avoid that in our framework. Okay, so after talking about the data engine set, next let's talk a bit about generation in simulation. First, it's about virtual reactions in a closed loop training or test for controllable behavior generation. So actually in our work, we have been trying to generate pretty safety critical and interactive behavior in closed loop so that we can create pretty challenging situations for our ego agent to be tested or trained. And the surrounding agent could be with different kinds of intentions as well as criticality levels. And for diffusion models, it could also be pretty computationally expensive, and we are also trying to optimize its computational efficiency with some other work. And diffusion models can not only be used for behavior, controllable behavior generation, but also editable sensory generation. But the problem, one of the major problems for a diffusion model at this stage would be the 3D consistency. It contains the context of the consistency across different views of the cameras, as well as the across modality 3D consistency for point cloud as well as cameras. So we propose some novel methods based on diffusion models to generate pretty consistent 3D scenes for both camera and LiDAR, conditioned on the input of 3D bounding boxes as well as the text. And from the results, you can clearly see we can generate the we can guarantee 3D consistency with even some styles, like ringing kind of styles. And we can also make it more editable with scene editing by reducing the number to a half. And we can still generate pretty good performances, as you can see in the generated data. And if we want to further improve the performances, we could even put one of the modality as the input together with the 3D bounding boxes and generate the other modality with our model. So soon we will be like releasing the corresponding papers. Okay, so after talking about how we can employ diffusion model in the editable generation context, next let's talk a bit about 3D reconstruction and novel view synthesis. There are many powerful tools in this domain, including NERV as well as 3D Gaussian splatting, which can take into account multimodal streams, try to parameterize that into some machine learning model, and generate pretty photorealistic camera views given the corresponding poses or the position. So actually, Gaussian splatting is showing pretty strong potential with the explicit representation for the editable feature, as well as its like capability to take into account large-scale driving scenes. And there are a lot of interesting work to apply that into the driving domain. But one of the problems would be there has to be some 3D bounding box annotations to help us decompose the dynamic obstacles from the static scene. So our question would be how we could remove that tedious 3D annotations and replace that with more self-supervised learning way directly from the videos so that we can work towards a scalable 3D aware world model. And that's why we propose this self-supervised street Gaussian for autonomous driving. And in this video demo, you can see that our proposed methods can construct pretty photorealistic camera rendering for reconstruction and novel view synthesis, compared with the vanilla 3D Gaussian splatting on the top. And we also compare with a number of state-of-the-art methodologies in our paper. And we can show pretty superior performances, even compared with those with 3D annotations. And it also attracts a lot of attentions in the open source world. And after talking about how Gaussian splatting could facilitate large-scale outdoor driving scene, next let's talk a bit about the more fine-grained way in compositional text-to-3D generation. So actually, when we provide a sentence with multiple objects, as well as its like physical interactions or some spatial relationship between them, actually it's a pretty hard kind of task with a lot of problems like object missing, semantic shift, or multi-phase problems. And that's why we try to construct a framework by exploiting many kinds of foundation models, including text-to-image, large language models, SAM, as well as stable diffusion, so that we can construct a training pipeline for 3D Gaussian with both single entity level as well as the composition level training. And actually, in the qualitative comparisons with many state-of-the-art methodologies, you can see that when there is a sentence combined with multiple objects as well as their like relationship, we can generate pretty accurate like 3D generation compared with the other methods. And more examples can be shown at the bottom of this slides. And finally, I will just cover a bit about like how large language models could be utilized for diagnosing conventional motion planners. Actually, when taking into account the differentiable stack in closed loop, many of the companies would still use some conventional planners or controllers in receding horizon to smooth the corresponding trajectory or perform some final verification. And actually, when we ask some question to ChatGPT to generate some Python code for us with either A-star search or like LQR, it can do a pretty good job. So that's why we are thinking about leveraging such capability in the diagnosis of the conventional planner. And we constructed a framework like this. When we have a conventional motion planner right here, we can take some key components from it to construct some like a planner describer combined with a quantitative evaluator to tell us how good or how bad this planner performs in different kinds of driving scenes. And we can also like take into account some system prompt altogether to construct this prompt set for our large language models to generate the corresponding diagnosis, prescriptions, as well as the patch program for us to not only improve our motion planner in the current iteration, but also generate some feedback for the next iteration. And here are some examples by utilizing critical scenario in common role benchmark to improve some imperfect planner. And in the results, we can see that at the first iteration, we can significantly improve the corresponding cost by identifying a few missing terms in the cost function. And actually, when it goes to the third iteration, we can drop the cost function into a relatively satisfactory level by identifying some pretty fundamental and inherent kind of problems. And we can obtain relatively good performances for such kind of critical situation. Okay, so here are some like quick summary as some takeaways for the industry. AI is definitely revolutionizing both the onboard stack as well as the development pipeline for autonomy development. And actually, multimodal foundation models is definitely becoming crucial for the development pipeline, such as data curation, mining, as well as the editable generation, diagnosis, etc. And language modality, especially those within the multimodality foundation models is making the differentiable stack to be more generalizable by bridging the internet scale data, as well as enhancing the capability of reasoning with the behavior and scenes. And closed loop simulation is definitely a key for the training and testing of the differentiable stack with enhanced and reactive data generator powered by the generative AI, as well as the node view synthesis and 3D reconstruction. So they are also being merged. And finally, the closed loop AI stack has to be trained with the some way beyond the imitative paradigm. And actually, we have to consider how we can deal with under demonstrated requirements as well as out of distribution cases. So that will conclude my talk. Thank you very much for your time and attention.